Welcome to this coding tutorial. Today, we're diving into LeetCode problem number 804, unique Morse code words. In this problem, we'll explore how to translate words into Morse code and identify unique transformations. Stick around as we break down the solution step by step. In this problem, we are tasked with finding the number of unique Morse code representations for a given list of words. The International Morse code provides a standard mapping for all 26 lowercase English letters, where, for instance, A maps to dot dash, B maps to dash, C maps to straight-face to, and so on. For example, if we take the word gin, its Morse code representation is formed by combining the Morse codes for G, I, and N, resulting in dash dot. Similarly, the word zen translates to dash. The goal is to write a function that computes how many unique Morse code representations exist among all the words in the input array. Each word in the list can be transformed into its Morse code equivalent by concatenating the Morse code representations of its individual letters. These mappings are predefined and provided as an array in the problem. Now, let's break down the input and output formats. The input is an array called words, which is a list of strings. Each string consists of lowercase English letters, and the length of each word in the array ranges from 1 to 12. Additionally, the total number of words in the array does not exceed 100. The output is a single integer representing the number of unique Morse code representations across all the words in the array. For example, if the input is words equals gin, zen, gig, message, the output would be 2 because there are 2 distinct Morse code transformations among these words. Here's the explanation for the first example. The word gin converts to the Morse code, dash dot, zen becomes, dash, gig is transformed into, and message also maps to, As we can see, both gig and message share the same Morse code representation, so they are not unique. In total, there are 2 unique Morse codes, dash dot and dot. Now, consider a second example where the input is words equals, A, B, C, D. Each of these words maps to a distinct Morse code, dot dash, dash, straight-face dot, and dash. Since all of these are unique, the output is 4. For the second example, the explanation highlights that each word has a distinct Morse code. The word A translates to dot dash, B to dash, C to straight-face dot, and D to dash. Because no 2 words share the same Morse code, all 4 transformations are unique. The constraints of the problem ensure that the array words will always have a size between 1 and 100, and each word will have a length between 1 and 12. Additionally, all words will consist solely of lowercase English letters, which guarantees that we can directly use the provided Morse code mappings without needing to handle special cases. Finally, let's consider some edge cases. If the words array contains only a single word, the output will always be 1 since there is only one Morse code representation. On the other hand, if all the words in the array map to unique Morse codes, the output will equal the number of words in the input. Conversely, if all the words map to the same Morse code, the output will be 1 as there is only one unique transformation. The problem constraints ensure that no word will be empty, so we know each word will contain at least one letter. These edge cases help clarify how the number of unique Morse codes depends on the structure of the input array. When tackling the problem of finding unique Morse code representations, the most intuitive approach is a brute force method. Here, we directly map each letter of the input words to its Morse code equivalent using a predefined mapping. For every word in the input, we iterate through its characters, translate each character into Morse, and concatenate these translations to form the word's complete Morse code representation. To ensure we only count distinct translations, we store each unique Morse code in a set, which handles duplicates automatically. While this approach is simple and straightforward to implement, it does come with some inefficiencies. The repetitive lookups required for each character and the frequent concatenation of strings add overhead to the process. In terms of complexity, this method operates with a time complexity of O, n asterisk k, where n is the number of input words and k is the average length of each word. The space complexity is O, U, where U represents the number of unique Morse translations. While easy to understand, this approach suffers from redundancy in operations, which we aim to address with a more optimized solution. A more efficient approach involves optimizing the brute force method by reducing unnecessary computations. Instead of repeatedly building strings for every letter and joining them for each word, we use a direct mapping technique combined with a hash set. First, we store the Morse code for all 26 letters of the English alphabet in an array. This allows us to translate each letter of a word into its Morse code through direct indexing, which is faster and avoids repetitive operations. For each word, we iterate through its characters, convert them to Morse using the mapping array, and then store the resulting translation in a set. The set ensures that only unique translations are kept, eliminating the need for additional checks for duplicates. This approach is deterministic and systematic, making it not only more efficient but also easier to manage. In terms of complexity, the time complexity remains O(n*k), as we still process each character of every word. However, the efficiency gains come from the reduced overhead of string operations. The space complexity is O(u), as we still store only the unique translations. This approach strikes a better balance between simplicity and performance. This optimized method relies on the assumption that the Morse code mapping for the English alphabet is fixed, a constraint that holds true for this problem. Based on its balance of efficiency and clarity, this is the approach we selected as the final solution. It simplifies the logic by utilizing direct array indexing for Morse translation and the unique properties of sets to handle duplicates. This choice is supported by several reasons. First, the mapping process is straightforward, making it easy to debug and verify the implementation. Second, the solution is efficient, with a time complexity of O(n*k), which scales well even with larger input sizes. Finally, space usage is minimized since we only store the unique Morse code translations in the set. Compared to the brute force approach, this method avoids redundant string operations and reduces computational overhead. While there are alternative data structures, such as hash maps, sets are particularly suitable here because they inherently manage uniqueness, simplifying the implementation further. Overall, this approach offers a clear and optimal solution to the problem. The solution's efficiency and correctness rest on the assumption that the Morse code mapping is fixed, which is guaranteed by the problem constraints. While the space complexity is slightly higher due to the need to store unique translations, this trade-off is acceptable given the gains in simplicity and performance. The code implementation follows this optimized approach step by step. First, we define an array containing the Morse code for each letter of the alphabet. Then, for each word, we construct its Morse translation by iterating over its characters, using the mapping array to convert each letter. These translations are stored in a set, ensuring only unique representations are counted. Finally, the function returns the size of the set, which represents the total number of unique Morse code words. This solution is both elegant and efficient, leveraging the problem's constraints to minimize computation while maintaining clarity and correctness. In this problem, the objective is to convert a list of words into their Morse code representations and determine how many unique transformations exist. Each word in the input consists of lowercase English letters, and we use a predefined mapping that assigns a specific Morse code sequence to each letter from A to Z. For example, A corresponds to .dash, B to dash, and so on. To solve this, we first understand the mapping provided, which can be stored as a list or dictionary for efficient lookups. Next, we parse the input, which is a list of words, such as gin, zen, gig, message. To track the unique transformations, we initialize a set called unique_transformations. A set is ideal here because it automatically eliminates duplicates, allowing us to focus only on distinct Morse code sequences. This forms the foundation for our algorithm. Now, we process each word in the input list step by step. For each word, we start by initializing an empty string to hold its Morse code translation. Then, we iterate over each character in the word. Using the predefined mapping, we fetch the corresponding Morse code for each character and append it to the translation string. For instance, consider the word gin. The letter G maps to dot, I maps to, and N maps to dash dot. When these are combined, the full Morse code translation for gin becomes dash. Once the translation string for the entire word is ready, we add it to the set of unique transformations. This ensures that only distinct translations are stored. Finally, the result is determined by the size of this set, which gives the count of unique transformations. For example, with the input gin, zen, gig, message, the set might contain transformations like dash and that, resulting in a count of 2. Several key insights help us refine this algorithm. First, the use of a set ensures that we don't need to manually check for duplicates, as it automatically handles uniqueness. Second, the predefined mapping of Morse codes can be stored as a list indexed from 0 to 25, corresponding to the letters A to Z. This allows for constant time lookups when translating each character. Third, each word is processed independently, and the translation process is linear in the length of the word, making this approach efficient and scalable. It's also important to consider edge cases. For instance, if the input list is empty, we would return 0 since there are no transformations. If there's only one word, the result is 1, as there's only one transformation. Similarly, if all words in the input are identical, the result is also 1 because all transformations are the same. Lastly, using minimal yet effective data structures like sets and lists balances memory usage and computational efficiency. Analyzing the algorithm's complexity gives us a clearer picture of its performance. For time complexity, translating a single word involves iterating through its characters, which takes O(m), where m is the word length. Translating all n words in the input list results in a total time complexity of O(n*(m). Adding each transformation to the set is an average O(1) operation, so it doesn't significantly impact the overall complexity. On the space complexity side, the set used to store unique transformations may grow to hold up to n entries in the worst case, contributing O(n) space. The predefined mapping, stored as a list or dictionary, uses a fixed space of O(26), which simplifies to O(1). Combining these, the total space complexity is O(n). The pseudocode for this algorithm illustrates how the mapping is used to translate words and populate the set, and ultimately, the function returns the size of the set as the result. To optimize this solution further, we can leverage several strategies. Since the Morse code mapping is fixed, we can pre-compute and store it as a list for constant time lookups, avoiding any redundant computation. Additionally, instead of using intermediate variables to store the translation, we can directly insert the generated transformation into the set, streamlining the process and reducing memory usage. For edge cases, we can implement early exit checks to handle scenarios such as an empty input list or all identical words, saving unnecessary computation time. These optimizations ensure the algorithm remains both efficient and easy to maintain, even for larger input sizes. This Python implementation solves LeetCode problem number 804, unique Morse code words. The goal is to determine how many unique Morse code transformations can be generated from a given list of words. We begin by defining a class solution containing the method unique Morse representations. Inside this method, we first define a list Morse_map, which contains the Morse code mappings for each letter of the English alphabet, A to Z, in order. Each index corresponds to the position of the letter in the alphabet, e.g., index 04, index 14b, and so on. Next, we create an empty set called unique_transformations. A set is used here because it automatically handles duplicates, ensuring that only unique Morse code transformations are stored. We then iterate through each word in the input list words. For each word, we use a generator expression to translate each character to its corresponding Morse code. The expression Morse_map, ord, char, ord, a, computes the index of the character in the Morse_map list. The ord function retrieves the ASCII value of the character, and subtracting ord, a, aligns it to the zero-based index of the alphabet. The transformed characters are concatenated using .join, to form the full Morse code transformation of the word. This transformation is then added to the unique_transformations set. Finally, we return the size of the unique_transformations set, which represents the number of distinct Morse code transformations. This solution is efficient with a time complexity of O(n*(m), where n is the number of words and m is the average length of the words. The space complexity is O(n), for storing the unique transformations in the set. This approach handles all edge cases, such as duplicate words or words of varying lengths, making it robust and production-ready. This is the Java implementation for LeetCode problem number 804, unique Morse code words. The logic mirrors the Python implementation, converting each word into its Morse code representation using a predefined mapping. Java-specific elements include the use of a hash set to store unique transformations and type declarations for variables. The solution iterates through each word, constructs its Morse code equivalent, and adds it to the set to ensure uniqueness. Finally, the size of the set is returned as the result. To begin solving this problem, we first need a way to translate each letter into its corresponding Morse code. This is achieved by defining a Morse_map list, where each index represents a letter of the alphabet, starting with a map to dot dash, b to dash, and so on. This mapping ensures we can efficiently look up the Morse code for any letter. Next, we prepare a set called unique_transformations. This set will store the unique Morse code representations of the words as we process them. Using a set is crucial because it automatically handles duplicates, ensuring that only distinct transformations are counted. Now, we start processing the words in the input list, beginning with the word Jin. For each character in Jin, we retrieve its Morse code representation, G maps to dot, I maps to, and N maps to dash dot. These are then concatenated into a single string, dash dot, which represents the Morse code transformation for Jin. This transformation is added to the unique_transformations set. Continuing with the next word, Zen, we use the same process. The characters Z, E, and N map to, that, and dash dot, respectively. When concatenated, they form the transformation, dash dot. However, since this exact transformation is already in our set, no new entry is added. Moving on to the word gig, we map G to dot, I to, and again G to dot. Concatenating these gives, dot, a new transformation that is added to the set. Finally, for the word message, we map M to, S to, and G to dot. This results in the transformation, which is identical to one already in the set, so no further addition is made. At the end of this process, our set contains two unique transformations, dash dot and dot. The size of the set is 2, which is returned as the result. Now, let's process a simpler example with the words of B and C. We begin by initializing the Morse_map and the unique_transformation set, just as before. For the word A, the transformation is dot dash, which gets added to the set. Next, B maps to dash, expanding the set to include both dot dash and dash. Finally, C maps to straight face, further adding to the set. With 3 unique transformations in total, the size of the set is 3, which becomes the output. In another example with the words hello and world, the process is similar. Hello transforms to dash, dash, which is added to the set. World transforms to dot 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 dash dash, introducing another unique transformation. The set now contains 2 transformations, so the output is 2. Key observations here are that the efficiency of the solution comes from processing each word character by character in O(n) time. By using a set, we ensure duplicates are handled automatically, and the mapping step is optimized by leveraging the ORD function to calculate indices for the Morse_map. This approach is both simple and effective for solving the problem. To analyze the time complexity of our solution, let's break it down into distinct steps. First, we have the initialization of the Morse code mapping. This mapping consists of a predefined list of 26 Morse code strings, which is a constant operation and takes O(1) time, as it doesn't depend on the size of the input. Next, we process the input list of words. If the input contains n words and the average length of each word is k, we iterate through each word and its characters to construct the corresponding Morse code transformation. Mapping a character to its Morse code is an O(1) operation using the ORD function, and constructing the transformation involves concatenating up to k strings for each word, making this step proportional to O(k) for one word. When considering all n words, the total cost for this step becomes O(n*k), as both the number of words and their average length contribute to the runtime. Now, let's consider the set operations. Each Morse code transformation is added to the unique_transformations set. Adding an item to a set is an average O(1) operation, so for n words, the total insertion cost is O(n). When we combine this with the time spent on constructing the Morse code transformations, the overall time complexity of the solution becomes O(n*k), where n is the number of words and k is their average length. Moving on to the space complexity, we first account for the Morse code mapping itself. The Morse_map is a constant list containing 26 fixed strings, so it requires only O(1) space. However, the unique_transformation set, which stores the distinct Morse code representations of the words, can grow depending on the input. In the worst case, if all n words have unique transformations, and each transformation has a length proportional to k, the set requires O, n asterisk k, space. Beyond the set, we also temporarily store intermediate transformation strings during the computation for each word. These strings are not stored permanently, instead, the memory is reused for each word, meaning they do not contribute to the overall space complexity. When we sum up all the contributions, the total space complexity is determined to be O, n asterisk k. To put this into perspective, a brute force approach to solving the problem might involve generating and comparing all possible combinations of Morse code strings against the input words. This could quickly become computationally infeasible as the input size grows. The current solution is far more efficient because it directly maps characters to their Morse code equivalent and leverages the efficiency of a hash set to ensure uniqueness, avoiding redundant computations. Finally, let's analyze the best, average, and worst-case scenarios for this solution. In all cases, the time complexity remains O, n asterisk k, as the solution must process every word in the input and compute its transformation, regardless of how the words are distributed. Similarly, the space complexity is O, n asterisk k, in all scenarios because the worst case assumes that all transformations are unique and must be stored in memory. To justify this big O notation, we can focus on the nested loop structure. The outer loop iterates through n words, while the inner loop processes up to k characters for each word. Multiplying these together gives O, n asterisk k, for the time complexity. For space usage, the primary contributor is the set that holds up to n unique transformations, each of size O, k. These mathematical evaluations confirm that the solution is both time and space efficient with a complexity of O, n asterisk k. When solving this problem, there are a few common mistakes to watch out for. First, incorrectly mapping characters to Morse code is a frequent error. This can happen if you forget to confirm whether the input assumes lowercase letters or if you make typos while setting up the Morse code dictionary. It's crucial to double-check the predefined mappings to avoid these issues. Next, not handling edge cases can lead to incorrect results. For example, you need to account for inputs like empty strings, single-character words, or words with repeated characters. Testing these scenarios ensures your solution is robust. Another pitfall is overlooking duplicate word transformations. The goal is often to identify unique Morse code transformations, so make sure your implementation accounts for duplicates. Finally, using inefficient approaches for large inputs can be problematic. If you rely on nested loops to process words, you might end up with O, n squared, complexity, which doesn't scale well when inputs are large. Instead, focus on optimizing your approach for better performance. Now, a subtle but significant mistake is not using a hash set to ensure uniqueness. Some may use a list to store Morse code transformations, but this results in O, n squared, complexity for checking duplicates. A hash set, on the other hand, provides O, 1, average time complexity for insertions and lookups, making it much more efficient. Another common issue is overcomplicating the solution. While it's tempting to write extensive code with multiple helper functions, simpler approaches are often better. For instance, Python's built-in join and set functions can make your code more concise and easier to debug. From an interview perspective, this problem tests several key skills. It evaluates your ability to pre-process data, such as mapping characters to Morse codes, and your effective use of hashing or sets for uniqueness. Scalability is another focus. Interviewers might ask how your solution handles larger inputs, so you should be prepared to discuss optimizations. Clear communication is also important. Be ready to explain your thought process, such as why you chose certain data structures or how you addressed edge cases. Lastly, anticipate follow-up questions. These might involve handling uppercase letters, additional character sets, or even transforming numbers and symbols. This problem is closely related to several other LeetCode problems that test similar concepts. Examples include Problem 49, which involves grouping anagrams, Problem 290 on word patterns, and Problem 205 about isomorphic strings. Exploring these problems can help you build a deeper understanding of related techniques. When it comes to alternative approaches, the brute force method is one option. In this approach, you map each word to its Morse code and then check for uniqueness using a list. While simple to implement, it's inefficient for larger inputs because the uniqueness checks can take O, n squared, time. A more efficient alternative is to use a hash set for uniqueness. By storing the Morse code transformations in a hash set, you can perform uniqueness checks in O1 on average. This approach is not only faster but also demonstrates a strong understanding of hash-based data structures, which is often valued in interviews. Another alternative approach involves leveraging string manipulation libraries for a more streamlined solution. For instance, in Python, you can use the join function to concatenate Morse code characters and is set to ensure uniqueness. This makes the code concise and elegant, reducing the potential for errors. However, it does require familiarity with Python-specific features or their equivalents in other programming languages. Overall, choosing the right approach depends on the constraints and requirements of the problem, but focusing on efficiency and simplicity will always serve you well. That wraps up our solution to LeetCode problem number 804, unique Morse code words. We covered the problem requirements, explored our approach, and highlighted key takeaways. Thanks for watching. Don't forget to like and subscribe for more tutorials. See you in the next one. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!